Hello, and welcome to our session on doing subtraction in base 2 or binary systems. Our first option for doing subtraction in base 2 number systems is to mimic the base 10 model for subtraction. To do that, let's go ahead and review how we learned how to do subtraction in grade school. When we do subtraction, we subtract our least significant bits first, in this case 3 minus 7. But 3 isn't big enough to take 7 away from it, so we have to borrow from the next column or the next most significant digit. Here we'll reduce the number 2 to 1, and then we'll add 10 to 3 to get 13. And then we can take 7 from 13 and get 6. After that, we can then do the next subtraction and subtract 1 minus 1 and get 0. And as expected, 23 minus 17 is 6, using this basic subtraction method. When we try to repeat that in base 2, however, things get a little trickier. In base 2, we also borrow when we don't have enough to subtract from. Let's take a look at what this looks like. In the first column, we have 1 minus 1, which is 0, so we don't have to borrow anything. But in this next column, when we try to subtract 0 minus 1, we can't do that because there's not enough in 0 to subtract 1 from. So we'll try to borrow from the next column, but the next column has nothing in it either. It's a 0. So we have to go even further to the next column and borrow from the 1. To borrow from the 1, we reduce its value to 0. But now we have to ask, what have we just borrowed? Well, the answer is in base 2, in that fourth position there, that carries a weight of 8. So what we've actually just borrowed is an 8. And now we have to put that borrowed number somewhere. So we'll put it in the third column as a 4, and in the second column as 2 2's. Giving us 1 times 4 plus 2 by 2, which equals 8, identical to what we borrowed. Now we can proceed with subtraction, saying that 2 minus 1 is simply equal to 1. As we go to the third column now, we've borrowed that 1, so we can take 1 minus 1, which will give us 0. And then in the last column, we have 0 now, minus 0 equal to 0. And then in the column to the left of that, 1 minus 1 gives us 0. So the result of 11001 minus 10111 is just equal to 00010, which in base 10 means that 25 minus 23 is simply equal to the number 2. And that's exactly what we get here in this subtraction. But imagine the number of rules we would have to implement and what we'd have to do to implement this using digital circuits and combinational logic. It would get very complicated. So let's take a look at some other possibilities for doing subtraction in base 2. The next option would be to simply represent the leftmost bit as a positive or negative number. And we might choose to represent 0 as the most significant bit, to represent a positive number, and 1 in that most significant or leftmost bit position to represent a negative number. But then we've also introduced a multitude of problems. First, we have to consider all the different combinations and potential overflows of adding and subtracting. If, for example, if we add a positive number to a negative number, we have to know whether the negative number is bigger or smaller in its absolute value than the positive. And once we know that, that changes our interpretation of the result. So we can go on and on with this, but ultimately, while it sounds simple to use the leftmost bit to indicate the sign of a number, using this technique to do subtraction or add negative numbers simply involves way too many rules. And that would be okay if that were our only option, but wouldn't lead to a very optimized or very clean circuit design. So let's look at one last technique, called the 2's complement method. In this method, we'll express all positive numbers in base 2 as we normally do. Then we'll express all negative numbers by doing what's called the 2's complement technique. This involves flipping all the bits, 1s to 0s and 0s to 1s, and adding 1 to the result to come up with a representation of that same number in its negative form. And then we can add the numbers as normal in base 2, and if we get a negative number as the result, we'll have to perform the 2's complement again to understand what the meaning of that number is in base 2. Let's take a look at a few examples here. First, with positive 3, we know in base 2 positive 3 is just 0, 0, 1, 1. To get the 2's complement of that number and therefore represent negative 3 using the 2's complement method, we just flip all the bits, 0 to 1 and 1 to 0, and add 1. When we do that, we get negative 3 represented as 1, 1, 0, 1. Now notice the leftmost significant bit turns out to be negative, or 1, indicating that it is indeed a negative number. But it's not the straightforward conversion that we used in option number 2. This is the 2's complement method. Likewise, we can convert positive 2 to a negative number using 2's complement notation. First, we flip all the bits to get 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, and then we'll add 1. And when we do that, 1, 1, 0, 1 plus 1 will give us 1, 1, 1, 0, which represents negative 2 in 2's complement notation. Likewise, we can represent positive 1 as a negative, again flipping the bits and adding 1, gives us negative 1 as 1, 1, 1, 1. This represents negative 1 in 2's complement notation. We should now note that 3 bits in 2's complement can only accommodate the numbers 0, 1, 2, and 3, and negative 4, negative 3, negative 2, and negative 1. Now you may be tempted to think we can represent positive 4, but in 3 bits, 4 is 1, 0, 0. And this actually represents a negative number because the leftmost bit is 1, indicating that this number should be negative, even in 2's complement notation. And what number does it represent? Well, if we take the 2's complement, 0, 1, 1, and add 1, we'll get the 2's complement equivalent, and we get 1, 0, 0. So this number is actually negative 4 rather than positive 4. So with 3 bits, we can actually accommodate negative 4, but not positive 4. And that follows with 4, 5, and 6 bits, and so on. Now let's take a look at an example of actually doing a subtraction operation using the 2's complement method. Here we're going to take 3 minus 5, and that's equivalent to 3 plus negative 5. So let's do the conversion first before we perform the addition operation. Positive 3 is just 0, 1, 1, but we'll have to have that extra bit to express 5. We need 4 bits to express the numbers 5 and negative 5. And now positive 5 will be just 0, 1, 0, 1, but we'll have to convert to 2's complement to get negative 5. 1, 0, 1, 0 plus 1 gives us 1, 1, 0, 1, or 1, 0, 1, 1, and that's negative 5. Now we can simply add the 2 together, add 0, 0, 1, 1, and 1, 0, 1, 1, 0, 1, 1, and our result is 1, 1, 1, 0. Now, is this correct? Well, what number is this that we're representing? To find out, let's take the 2's complement again. The 2's complement gives us positive 2, which tells us that our result is actually negative 2, and that is correct because 3 plus 5 is actually negative 2. how 2's complement subtraction works. Now we can continue doing this for any type of number, subtracting by adding the negative of the second number to the first. But it's just important that we make sure we have enough bits to represent all our numbers. In this example, we'll need 5 bits to represent 8. 4 bits only covers positive 7 to negative 8, so we need to move up to 5 bits in order to capture positive 8. Positive 4 in regular base 2 notation is just simply equal to 100, but since we need 5 bits, we need to pad the left with 2 more zeros. Now to get negative 4, we can take the 2's complement, flip the bits and add 1. 1 and 1 is 0. Carry 1, 0, 1, 1, 1. So negative 4 is just 1, 1, 1, 0, 0. And positive 8, which is the second number we're handling in this operation, will just be 0, 1, 0, 0, 0, putting 8 in the 1 in the fourth weight spot here. And then we can add the 2 together, negative 4 in 2's complement notation, plus 8 to get the result. And our result when we add negative 4 plus 8 is 0, 0, 1, 0, 0, which is equal to positive 4 in base 10 and is the correct result. Now notice if we had included the overflow bit here, 1, which we got as the carry out of the last operation, our subtraction operation wouldn't have worked. So when we're adding two 5-bit numbers, we can only consider those 5 bits in the result as representing what the true result is of the subtraction operation. If we overflow and try to add 2 numbers that end up in a result that actually requires 6 or more bits, we'll end up with an incorrect result. And we'll have to deal with that in the implementation of this subtraction method using digital circuits. So what we've done here is we've introduced the 2's complement method to provide a reliable, consistent, and uncomplicated way to represent negative numbers in base 2, and therefore to subtract any 2 numbers using this method. While other methods require a cumbersome set of rules to implement, the 2's complement is straightforward to implement using digital circuits, and we'll take a look at that in later sessions. Well, that's all for the process of subtraction in base 2 today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.